Hello, everybody. Can you hear me clearly? Okay, cool. Okay, one moment, please. Um, Hello, everybody. My name is Trung-Kien Chan. This is a joint work with our colleagues in Post Center for Artificial Intelligence and Max Planck Institute of Informatics in Germany. Our motivation is that there are many large knowledge graph like Freebase, Wikidata, ConceptNet, and you can name it or you can see it here. They are created via crowdsourcing or automatically constructed or semi-automatically constructed. And it's very likely that they contain error. Detecting error in large knowledge graph is important and challenging task. It is important because it has impact on the application consuming knowledge graph directly or on algorithm operating on knowledge graph for some other task like link prediction or reasoning. It is challenging because of the size of the knowledge graph. And here is one example in DBpedia. This information is about the entity Roberta Weiss. She is an actress and she has two spouses, Alberta and Roscoe Bond. If we click on Alberta, we will see that this entity has a type settlement, which is not a person or not a human. So there might be some error here. When we look at the Wikipedia page, we see that actually Roberta Weiss was born in Alberta, and she only has one spell, which is Roscoe born. So this is indeed an error in DBpedia. So how we detect such an error in large-scale knowledge graph? In this work, we propose to use the background knowledge or ontology. An ontology is a set of constraints, and we can validate knowledge graph on this constraint. So the problem statement of our work will be like, given a knowledge graph G and an ontology O, the task is to check whether G is consistent with respect to O or not. If it is not the case, we compute all explanation for the inconsistency. By inconsistency explanation, I mean this is a smallest subset of G and O in which contradiction occur. And below the slide is a simplified example of the error with us seen in previous slides. And this is an overview of our approach. Given the input knowledge graph, in the first step, we split the knowledge graph into different modules. And since there are many similar modules, we want to go in one step further by abstract the module to only collect the similarity between them and operate on the representative module. And the result of this step we call it the abstraction. And instead of computing inconsistency explanation directly on the input knowledge graph, we do it on the abstraction together with the input ontology. And then in the last step, we reconstruct the explanation for the input knowledge graph. Please raise question at any time if you have. So before going to the detail of our approach, we would like to mention the language we consider in our work. Is it a subset or is it a fragment of the web ontology language? It is very common in semantic web community or knowledge representation and reasoning community. And here we define relation, we define classes or complex type, and we define what axioms are allowed in our ontology. This is a compact form of the language. The language can express So, okay, so this is the first step in our approach, which is split the knowledge graph. Can you still hear me? I received something like my internet connection is not so stable. Okay, I'll just continue. So what we mean by module, so given the input knowledge graph here, we define the module for each entity in the knowledge graph. The module for one entity is a subset of the knowledge graph in which that entity occur. For example, the module for Toyota is a triple, like Microsoft has client Toyota, and Toyota is a city of Japan. And this is rated as like Toyota has a Thai popular name. Similarly, we can have the module for Bosch and also module for Germany. And given the language we present in the previous slide, we can prove that it has a locality property. This means that for any ontology, consistency checking on the original knowledge graph can be reduced to consistency checking over the all module of this knowledge graph. And this locally property enable us to run parallel or incremental algorithm, but there are still so many modules because as you can see, the number of modules is equal to the number of entity in the knowledge graph. So our solution is to abstract and to process multiple modules at the same time. And how we do that? We base on so-called local type. Sorry. We define local type as a tuple contain 3 elements. The first one is a set of type of that entity. The second element is a set of incoming relations. And the last element is a set of outgoing relation. For example, we have local type of Toyota equal to local type of Bosch and equal to this tuple because Bosch has a Thai popular name, Toyota has a Thai popular name, it has incoming relation, has client, it has outgoing relation, city of. And for each local type, we construct a so-called abstraction. And what it look like this. For this local type, we compute some kind of abstraction, and it is indeed another knowledge graph, but this is very small. We create an entity which is the instance of popular name. It has incoming relation, has client, and outgoing relation, city of. And we call this is the abstraction for 2 modules of Bosch and Toyota. So as you can see here, this abstraction represents many entity or many tuple in the original knowledge graph. And now we go to the next step to compute explanation for inconsistency if it occurs, but not directly in the input knowledge graph, but on the abstraction. Suppose we have the input ontology like this. Property range has client company, property domain, city of city, and disjoint classes company, city, and country. And we can see that we can compute explanation for it. It contains 2 tuples. W has client V, and V is city of U. Why it is an explanation and why it's trigger contradiction? Because from the tuple W has client V and property range has client company, we can infer that V has a type company. And from second tuple V is city of U, and the axiom in ontology property domain city of is city, we can infer that V also has the type city. And due to the last axiom here, we have company and city are disjoint classes. Therefore, we derive the contradiction. And we call this the pattern for inconsistency explanation. Why we call it a pattern? Because this represents many other concrete explanation in the original or in the input knowledge graph. For example, we can, from this pattern, we can reconstruct the explanation in the original knowledge graph by mapping V to Bosch, W to IBM, and U to Germany. Similarly, we can have another explanation where we map V to Toyota and W to Microsoft and U to Japan. And doing this way, we can indirectly compute explanation for inconsistency of the input knowledge graph with respect to the ontology. So we evaluate our method on several data sets. We have Yago, DBpedia, and NPD. Yago and DBpedia, you might already know them because they are quite popular and well known. NPD is another data set about Norwegian petroleum directory. So it's kind of a knowledge graph about petroleum activity in Norway. And we have two baselines here. The first one, we use the explanation reasoner, which use pellet underlying. And the second one is a modularization setting in our approach. And for the statistic of the data set, you can see here, the knowledge graph is quite large. It has from some 1,000 to a million tuple. And this is the number of axioms in the ontology. This is number of entity, number of classes, and number of relations. And this is the result of the baselines and the result of our approach. Our approach have in two settings. First one is modular, and second one is the abstraction. And as you can see here, in the setting of abstraction, we regard each abstraction is a module. And as a result, pellet cannot process the whole knowledge graph at once. And splitting the input knowledge graph into modules already have to obtain some result, but not so many. And finally, our approach can detect many explanations for inconsistency. The more, the better. And here in this slide, I just want to present or give you some intuition about the distribution of the pattern for just inconsistency explanation. Here is kind of first 10 pattern for it. And the first pattern account for more than 50% of the explanation for inconsistency, for example, in DBpedia, which means that there are some common patterns which cause or which lead to the error in the knowledge graph. And here is some concrete example for Yago and DBpedia. On the first column, you can see the pattern. On the second column, you can see which ontology action together with this pattern trigger contradiction. And in the last column, you can see the real or concrete example of explanation in the input in Yago or in DBpedia. And in our paper, if you just click to this text, and it will link directly to the entity, and you can easily see it as you see in the first example of DBpedia. So to summarize, we propose a scalable symbolic reasoning approach to compute inconsistency explanation for large knowledge graph. And moreover, the explanation are grouped into patterns, and which could reveal the systematic error of the knowledge construction process. And our approach worked for a practical fragment of the popular web ontology language. And this concludes my talk. Thank you very much for your attention. I'm happy to answer any question. Are you still hear me? Can you hear me?
Yes. Thank you for the talk. Can you hear me?
Are there any questions? Uh-huh. Okay. So after modularization, actually we split the knowledge graph in. Should I read the question loudly so everybody can hear, or I just answer it because I see it in the chat, not in the. Okay, the question is, how can you preserve completeness after modularization? Is it possible that a large knowledge graph cannot be reduced to small modulars? For the first part, we guarantee that completeness can be achieved because there are some property in our modularization part. I can go back to the slide. So if you look at the abstraction, you can see that there is a homomorphism from the abstraction back to the original knowledge graph, but there are no homomorphism from the input knowledge graph to the abstraction. But we can prove that when we have so many, when we compute all abstraction of the module, and then we can add more link abstraction to connect them to regain the structure of the input knowledge graph. And under the consider language, we can guarantee that adding new edges or new tuple to the abstraction does not introduce any new entailment. And from that, we can also construct a homomorphism from the original knowledge graph to the abstraction. And that's how we obtain or we gain completeness. And for the second part of the question, is it possible that a large knowledge graph cannot be reduced to a small module? It is possible, depend on which ontology language you're considering. For the language in our work, it always the case. And also depend on the input knowledge graph. If you consider very small input knowledge graph, and it could be that the module or the abstraction bigger than the input knowledge graph, but in our test or in general for large knowledge graph, the abstraction are typically smaller. So did I answer your question? Okay, great. Thanks. So I think if there are no questions, okay. So I think I start earlier, so there are plenty of time for question. And the host just told me to keep the Q&A until 11:45. So you can relax and think about question or chat, just chat.
Wait, hello?
Hello.
Yeah, I have two questions.
Mhm.
Can your this model apply to very big knowledge graph? What's the time complexity here? I mean, very huge knowledge graph.
Depend on how you consider what is a huge knowledge graph. In the test, in our experiment, we tested with the knowledge graph range from 1,000 to 22 million of people, and regarding the running time, it take like 21 hours to process the largest knowledge graph, and for larger knowledge graph or huge knowledge graph, we need to test more.
Okay.
Yeah.
Okay, I have another question. So, what if there is a lot of wrong facts or some we call noise or some missing facts? So, what will happen?
What do you mean by missing fact? We want to predict, or we want to what to do with missing fact here?
Yeah, and also if there are some wrong facts.
Okay, some wrong fact. Yeah.
Yeah.
This actually a very interesting topic, like what to do with the wrong fact, or what to do with the explanation we just computed. One way is to, if you can guarantee or you can see clearly that this is the wrong fact, then one way to do is just to clean it up, to remove it from the knowledge graph. And another situation is we have the combination of several triple or fact in the knowledge graph trigger the inconsistency. Then it is a bit tricky to decide which one is the wrong one and which one is the correct one. And this is not completely solved in this work. Yeah.
Okay, thank you.
Yeah, thank you too. Okay, so I will stop my sharing. Thank you very much again, and stay healthy. Have a good day. Bye-bye.